Alright, we are getting into the good stuff here. This is officially the first section of chapter 4. This chapter is big, so we're going to spend at least 2 to 3 days, probably 3 days, on just section 4.1. It's all about ionic compounds, but we really break ionic compounds into three different types. Today we're going to be starting with the simplest type, which is actually just called simple binary ionic compounds, which means we're just looking at two different things coming together. Later on in the coming days, we're going to be looking at 3 or 4 or 5 different elements coming together and seeing what we can do in terms of their name and formula. So hopefully you did your homework from yesterday, because we're going to be using a lot of that knowledge today in terms of how to name things, which we should have some good familiarity with, and developing the formulas, which is going to be a little bit newer for us today. So just to recap from yesterday, a little bit about ionic bonding. This ionic bonding always happens between a metal and a nonmetal. And when we have ionic bonding happening, it involves the transfer of electrons. So we talked a little bit about covalent bonding and how that involves a little bit of sharing of electrons. Ionic bonding isn't like that. Metals are dying to give up their electrons, and nonmetals are ready to take those electrons, and that makes them a very, very good pair. The metals are always going to be dishing out their electrons, the nonmetals are always going to be taking it. So there's always a transfer of electrons. What's interesting is the amount of electrons that is given up by the metal is always exactly equal to the amount of electrons received by the nonmetal. And that's pretty obvious. You can't send 3 electrons and get 4 electrons. That doesn't make sense. So the amount of electrons that the metal gives up is the exact same as the nonmetal receives. So just as always, to the teacher, please make sure they have enough time to copy, so just pause the slide to give them enough time to copy down what they need to. So this is an example we took a look at yesterday. Sodium was our metal, and our metal here wants to give up the electron. Chlorine has an empty spot. So what happens? Well, sodium is going to give up its electron to chlorine, and that's going to complete its valence shell, and it's going to give sodium a full valence shell because it lost that one extra electron. So because of that, sodium gave up an electron. It became positive, aka a cation. Chlorine accepted that electron, so it became negative, aka an anion. So they only happen between metals and nonmetals. Metals, of course, lose their electrons, they become positively charged. Nonmetals gain electrons, they'll become negatively charged, and this results in an ionic compound. So yesterday we did a ton of work on Lewis symbols, and this kind of recaps what we went over. So just take your time and copy that. Okay, when it comes to binary ionic bonding, this is an ionic bond, which means metal and a nonmetal, formed between two things, and that's what the word binary means. So if you think about binary code, it's just ones and zeros, so two things. If you think about a bicycle that has 2 wheels, binary means 2, so it's ionic bonding between two things. So let's take a look. We're going to start off with naming binary ionic compounds, which we did yesterday. Generally, this entire section only involves 2 things, naming and formulas, and you're going to get so good at doing these things. That's called nomenclature, which is just a really fancy way of saying names and formulas. So that's what we're going to be really investigating here, and like I said, today we're going to be starting with binary compounds. So they used to have a problem where everyone was naming these things differently. Eventually, all the big shot chemists said, we got to fix this problem. So what do? They came up with IUPAC, which is a standard way of naming things. Unfortunately, a lot of it is rooted in the Latin versions of the words and the chemicals. So especially as we get into the acids, you might see some interesting choices about how to name things, but it's the standard that everyone's doing internationally. So it works really, really well because there's a high level of consistency between the different nations doing this. Okay, so some rules just to recap yesterday. This is what we were going to be taking a look at today. So when we are naming things, you always write the name of the first element, which is always our metal, as it is on the periodic table, so you never touch it. So first we have in this, Al. So we would just write aluminum. Perfect. So write the name of the first element, that will be aluminum. Then, for the second element, instead of writing chlorine, we said yesterday that we want to replace that ending with IDE. So it's not aluminum chlorine, it would become aluminum chloride. So we drop that ending from chlorine to ide, and we get a wonderful name there, aluminum chloride. One thing to keep in mind, make sure you're writing that metal first. It always goes metal and then non-metal when we were talking about ionic compounds. Alright, and don't forget about that IDE ending. Lots of people do, so please make sure you are aware of that. Okay, next, if we take a look at lithium and bromine coming together, so LiBr, we have lithium, which is our metal, always written first, bromine, which is our non-metal, so we don't call it lithium bromine, we would call it lithium bromide. So we take out that INE, we change it to ide, and we have lithium bromide. So pretty easy to name these things. So go ahead, complete those practice problems there. I don't anticipate you having any big difficulties with those. Just make sure you get them done. That's really what I'm after there. The real challenge is going to be coming up with the formulas. That's always a little bit trickier for people. Maybe not so much in this section, but definitely Monday and Tuesday, it kind of throws people for a little bit of a loop. Okay. So not too much to talk about here. We looked at Lewis dot diagrams and we said, okay, if you don't have enough spots for electrons, we have to kind of bring in different atoms, so different numbers of atoms. So in this example, aluminum has 3 extra valence electrons, 1, 2, and 3. And if chlorine only can absorb 1 electron, well, that's no good because aluminum is still going to have 2 extra. So we have to bring 2 extra chlorine atoms for a total of 3, which exactly matches the number of valence electrons we need to move out. So to write the chemical formula, we could draw Lewis dot structures for every single thing that we wanted to do, but that would take so long and you would end up hating my guts, and I don't want that to happen at all. So what we've done, and what everyone's started to do, is develop this crisscross rule, which is a very, very quick shortcut method in order to make this a lot easier for you and will not have you drawing thousands and thousands of Lewis structures. Important thing to remember here is charge neutrality. We never want these compounds to have a net charge. So they should always have a net charge of 0. So we want them to be neutral. We don't want them to be charged either positively or negatively, which is why this crisscross rule is so important. So let's get into it. I'd like you right now to take out your periodic table because you're going to be using it pretty much on every question for the rest of this course. So, or sorry, for the rest of this unit. So definitely take that out now if you can. I'll give you a second to do that. Also, did you guys see that trade? Isaiah Thomas gone. Cavaliers. LeBron James is running the show over there, right? And D Wade back to Miami. That's crazy. Okay, oh, we should keep going. All right, crisscross rule. Let's take a look at these things. These are the rules. Don't worry about this. I'm going to break it down step by step. There's no point in me explaining it. The best way to do this is just to give you an example. So that is exactly what we are going to do right now. So let's start with step 1. Now we're going to take a look at analyzing magnesium chloride. So write the symbols of both the elements. First you want to write the metal, then you want to write the nonmetal. So we have those things right here. So the symbol for magnesium is Mg. The symbol for chlorine is Cl. So we have Mg and Cl. Write them right beside each other, and step 1 is done. So just take a look at your periodic table. What is the symbol for these things? And you write them down, and you are good. Now, for step 2, please take out your periodic table, have it right in front of you, because we are going to make some changes to your periodic table. And maybe not changes, but certainly addition. So the way this works is we have to figure out what is the ionic charge on each one of these elements on the periodic table. And that would be a big problem, except we just spent the last 2 days drawing Bohr-Rutherford diagrams and Lewis dot diagrams until you were probably sick of them. So why did we do that? Well, it's for this reason. If we take a look at all of the elements in group 1, we said that they had something very, very important in common. And that thing is that each of these elements here have a valence charge. So they have a valence electron count of 1. So if we drew the Bohr-Rutherford diagram or the Lewis dot diagram, every single one of these would have 1 extra electron. So what charge do they have? Well, what ends up happening when these things bond is they always give up that electron in order to become stable. So if they have 1 extra electron, they're dying to give this thing up. And when they do give it up, since they lose an electron, they have a charge of +1. Oh no! Oh, brutal. I had like all these animations here, guys. Okay, hang tight. Emergency. Why is that like that? Okay, hold up, hold up. What, can I make it disappear? 1 sec. You guys don't have a choice anyway, so 1 sec. About, oh, see that? Okay, that's cool. Okay. Pretend that never happened. Here we go. So, like I was saying, bring it back, here we go. All of these have a valence electron count of 1 electron. So they're totally dying to give up this electron, and when they do, they lose that electron. And that's an amazing thing, because when they lose it, they become less negative and acquire a charge of, there we go, +1. So if you can write on your periodic table above group 1, can you write that +1 charge? Which will tell us that every single element in this has an ionic charge of +1 during bonding. Great. Now if we take a look at group 2, well, based on patterns, these all have a valence electron count of 2. So they don't need to just lose 1 electron when they bond, they end up losing 2 electrons. So they're trying to give up 2 electrons, and when they do, they end up with a charge of +2. So please write that in. And we always skip these guys. We go right to group 13. And in group 13, all of these have a charge of +3 because they have 3 valence electrons. So please write the +3 above them. Now, you'll notice that we don't include these. We'll talk about those another day, but we definitely don't include the metalloids. And we don't include the metalloids because ionic bonding happens between a metal and a nonmetal. So we don't really talk about metalloids in terms of ionic bonding. That's a different type. Next, now we go to the nonmetals. And remember, metals are cations. Notice how they all have an ionic charge that's positive. Nonmetals will have an ionic charge that's negative because they form anions. See, if we take a look at nitrogen, nitrogen has 5 valence electrons. So its charge isn't +5 because it's not going to choose to give up 5 electrons. That's a ton of work. Instead, what it can do to fill up its valence electron count is instead of giving up 5, it can just take on another 3. And that's what the nonmetals do. They like to take on more electrons. So instead of getting rid of 5, they add an extra 3. And when you add 3 electrons, you have a -3 net charge. Oxygen, sulfur, selenium, same kind of deal, except now they're going to only add 2 electrons. And our halogens, which is this group right here, will have a -1. So please make sure you've written all that in. Now, when it comes to the noble gases, these guys completely do not care about bonding. They're super happy as they are. They don't need to make any movements in order to get a full valence shell. So these things have a charge of 0 because they're totally not interested at all. All right, so this is going to be very helpful for you. Please make sure you've got this copied down. It is very important. This will not be given to you on your periodic table during your tests, so I generally recommend the very first thing you do as soon as you get into a test or a quiz is take a pencil and write these numbers up at the top. Eventually you'll get good enough that you won't need to know these and you'll remember them, but for now, that's how we'll start. All right, so let's go to step 2. Step 2, it says find the charge for each of the elements using your periodic table and write the charges above each element. So if you take a look at magnesium, you would notice that it is in group number 2. If you take a look at chlorine, you'll notice that it is in group number 17. And if you take a look at the number you wrote above those groups, they will give you the charges. So I'm just going to back that thing up for 1 second. We'll take a look at magnesium. Magnesium has a charge of +2, and if you find chlorine, chlorine has a charge of -1. See how easy this is? My gosh. So when we do that, awesome. We write the charges up top. Step 2 complete. So let's move to step 3. Step 3 is why we call this the crisscross method. So we are going to crisscross these charges, and we are totally never going to care whether they are positive or negative. So in the future, you don't even have to write that positive or negative sign. We're just doing it for the first couple just to make sure we got this thing down. So in the crisscross method, we have our magnesium 2+, our chlorine 1-. We are going to crisscross these things down. So we wrote them up top. In chemistry, you'll never see anything written above. Everything's always written below. Because what happens is we crisscross this 2 down to the bottom of chlorine. And now we have to crisscross this 1 from the top of chlorine all the way down to the bottom of magnesium. So we crisscross that thing down. Now when we crisscross them, that works out perfectly because what do we get? Well, now that's going to be magnesium, and it's going to take that 1 from chlorine. And the chlorine is going to take the 2, which is now going to be at its feet. So we're going to have magnesium 1, chlorine 2, and that's exactly what we get. So that 1 goes to magnesium, that 2 crisscrosses down to chlorine, and it is perfect. Well, it's not really perfect at all because we have this ugly 1 in here, yuck. So what we're going to do is we need to kind of reduce our fractions in a way. Oh, I love that word, fractions. And it's all about reducing it. So we look, are there any common numbers that we can divide by to make these things smaller? Well, they don't really divide by anything, so it's as small as it can get. So our very last step is to get rid of any 1s we see. We never write Mg1Cl2. We would switch that up and it would just be MgCl2. So that should be your final step there. And that's it. That's how we do formulas. That seems like a long process. You will get incredibly quick at that by the end of the day, I promise you. You won't need to do all those steps. In fact, I think it would be really time consuming if you did. But for the first couple and for the first 5-10 minutes of doing this, I would like you to do all the steps. So definitely on the next one, I'd like you to try completing all the steps to determine the formula for calcium oxide. So to the teacher, when everyone's attempted, please go ahead and advance the slide. I'm going to advance it now. Okay, so this is what you should have got for step 1. Write the formula, the chemical names for calcium and oxygen. We've done that. Step 2, you want to take a look at the charges. Calcium is going to have a charge of +2. Oxygen is going to have a charge of 2-. After that, we want to crisscross these things down. So that 2 is going to go at the bottom of oxygen. That oxygen, oh no, that oxygen 2- is going to go at the bottom of calcium. Perfect. And we will end up with Ca2O2, which is great except for one thing. We need to do some reductions. So they both have 2, which means we can divide both of those things by 2, and that ends up with Ca1O1, but we never want to keep those 1s hanging in there. So we will end up with CaO, and that would be our final answer. Okay, so try to solve for the first four problems. I will give you a minute to do that. So when everyone's ready, please just advance the slide. I will be advancing it now. So that's what you should have got. When you go through the process, these are the final answers. All three of these would have canceled out. Potassium sulfide, however, would not, and you'd be left with K2S. And when you are done that, I'd like you to complete all of the problems that I have given you in the next section. So I think it goes A to L is what we are looking for. So go A to L, try to complete those. The problems and sorry, the answers will be on the next slide for you. All right, so the answers are all up here. When you are ready, please take a look at those. You, for your homework, have a fair amount of homework. So there are two worksheets that should be in your book, in your package that you are working through right now. You should be able to see on the LMS the answers. I just checked. The answers to both worksheets are posted. There's also your first practice quiz on the LMS that is due by Monday. So I'm expecting everyone to have these two worksheets completed as well as the practice quiz by Monday. And it is all on these two things. It's on ionic compound naming and ionic compound formulas. If you have any questions with any of this stuff, please feel free to email me. MrValconi@gmail.com is where you can reach me. Please go through this video again if you need some help or clarification with any of the concepts, but this comes down to practice. You need to get this done, and you need to get this done well, because this is going to form the basis for the rest of chemistry. So if you struggle with this, we got to get that fixed up ASAP, Rocky. All right, you guys have a wonderful weekend. Please make sure you get the homework done. Stay safe. Get to church on Sunday.